here and work across again. Think of having that same region 2, 4, still revolved around the x-axis. Right, but now if I slice it this way when I revolve, right, so what my object basically being this trumpet-like funnel shape. This is being revolved around, especially if you look right here, and you'd expect to see something like this. And looking at it from the end, and what, if we move back some distance to where it hits the back edge. This here would be back at this distance to the front face. Here. You guys getting the 3D image okay with what I've drawn? Alright, so this object, right, then being essentially, you're taking like a, whatever, a tomato soup can or something, you take the lid and bottom out of it, right, you've got this hollow shell. So this is referred to as a shell. The shell method or whatever. But what's the volume of the shell? Just like we started there with the volume of the disk, we want to know what's the volume of the shell. If I think of this shell as having a height, much like I labeled the height there, a radius, R, and some, I'll call it thickness, T, right, then, well, what volume would be the distance around it times the height of it and its thickness. In other words, if you think of kind of splitting this down the side and unrolling it, right, you'd have a sheet that would what, have a dimension in here of h. Whenever you want to show the thickness, there would certainly be a thickness to it in here. So you'd still have some thickness. But what this dimension here, being the distance around this circumference, right, would be a 2 pi r. Right, so 2 pi r ht. Volume is 2 pi r ht. That's, I think, the best starting place. Much like I started here. All right, so the job is then going to be to, with this idea of a basic building block of a shell, looking at how the shell sits in this particular problem, again in the same manner of give yourself a fixed point for the general sort of shell. Remind yourself that this does have the y equals x squared relationship for all points there. Probably that's about all we need at the moment. Let's make some space and then build off of this idea. Right. Again, we're thinking about the thickness term. And this, what the thickness term would be in here. Right, and it would be in here, right? So that would be what since this is the y-axis, that would be equivalent to a dy kind of slicing. Right, that kind of gives you a start on how to change the name of this. Right, so we're going to say, since the thickness is really differential, the volume must be differential. So dv must then be 2 pi rh, and in our case, dy. Right, therefore, what the full volume is the integral of that 2 pi rh dy. And we want to just get r and h in terms of y. So let's see, r what? The radius of the can, this distance in here, right, would be what up in here? Yeah, it would be the same as this distance right here, right? It would be the radius, and that would be the same as the y coordinate. So I can say this is integral 2 pi y. What's h in this? H was the height of the shell. That's, we really need to label it in the 3D when it gets very confusing. You have a height measure in there. And what, in this picture, that's really this distance in here. That would be the height. And the height would therefore be? Yeah, it would be this full distance of 2 less this distance, but that's an x, right? This distance in here is an x. And the whole distance is 2, so 2 less x is the h distance that remains. Everybody okay with that? And that's a full distance of 2, that much is x, so what remains must be the 2 less the x. Alright, so that's then a 2 less x. Y. Alright, so I guess we're, got to convert the x to a y.
So.
And again, because we had this y was x squared, and we have x is the root of y. You do have a plus or minus there, but we're going to take the positive. We only have positive y's that we're working in, and we do want positive measures. So this is taken as the positive root. And so what? I'll take the 2 pi out. We've got an integral. We've got y. We've got 2 less root y dy. And the y's are going from 0 up to 4 if I picture where all these slices would sit here. So from 0 to 4. So hopefully, integrating that, we'll get that same 32/5. So what, we have a 2 pi integral of quantity 2y less y to the 3/2 dy. That's from 0 to 4. Process that. Let's see, we have a 2 pi times 2y becomes y squared. The minus 3/2 becomes a 2/5 of y to the 5/2. And evaluate the y's from 0 to 4. So I guess what a 2 pi want to be 4 squared less 2/5 of 4 to the 5/2 minus nothing. Both terms are 0 at 0. Don't assume that. Check it. You know, I see 0. Don't just, oh yeah, 0. You know, oh, it depends on the function. You know, that's a cosine. That ain't 0. Okay, because a lot of people, as soon as they see 0, they just write 0. Don't make that assumption. In this case, yes. Oh boy, what do we got here? 2 pi with 16 less 4 square root 2 fifth 32. So we have a 2 times 32 over 5. So we've got what? A 2 pi with 80 less 64 over 5. The 64 is 16. Oh, good. 2 pi right, times 16 over 5. Yes, that's the 32 pi over 5. All right, so it does work. See what fun you're going to have with fractions. You know, this being a simple one. So, real carefully, all the little details. But you can see that, you know, either the shells or the discs, right? When we added up all of these through the integral process, came up with that same volume. And that's, you know,
have happened. So we can use that. So I'm going to either method